In this video, we're going to be learning how to graph functions that have negative exponents. If you remember our exponent rules, whenever we have anything to the power of a negative number, we can rewrite this as something over 1. The negative exponent tells you to flip the fraction. So this is really 1 over x to the first power, or you can just write it 1 over x. So this is equivalent to a reciprocal function. Which looks like this parent graph. Power functions with negative exponents are undefined when x equals 0. Why? Well, if I put in 0 for x, we have 1 divided by 0, and we're not allowed to divide by 0. So you are looking for discontinuities that would make x equal 0, or the denominator equal to 0. Okay, so let's talk about end behavior and symmetry. When our exponent is even, so exponents, if it's even, it's symmetric about the y-axis. And if the exponent is odd, it's symmetric about the origin. Okay. So we want it to look kind of like this at the end. If we have an even power, so it's symmetric about the y-axis, and the leading coefficient is positive, that means this is my graph. Both the tails are going to point in the same direction because it's in a positive value. So we're going to have a function that looks like this. So both of them are kind of a mirror of each other on the y-axis. This one's going to be the same way, but since it's negative, it's going to be under the x-axis. Now these two are more like this one. So if we take this one out and the exponent is odd, and the leading coefficient is positive, so it'd be over here, it would look like this one. But if it was negative, everything would flip over the y-axis. So instead of looking like this, it would mirror onto the other side, looking like this and this. All right, let's do the first one. 4 times x to the negative second power. So we can do a rewrite as 4 times 1 over x squared. Or you write it this way, but this way doesn't really help me a lot, so I kind of ignore this way. This way we can graph this first part. We've got a positive coefficient and we have an even exponent. So positive even is going to look something like this top function. Let's plug in a value we know. If I plug in 0, it's not going to work. So 1 over 0 squared would be 1 divided by 0, so I can't do that. I can hop over to 1. 1 over 1 squared, so that's 1 over 1, times 4 would be 4. So I put a dot right there. If I plug in 2, 1 over 2 squared would be 1 over 4, and if I multiply that by 4, I get 1. If I kept plugging in values, eventually it's going to get really close to the x-axis, like so. And if I kept plugging like fractions in, I would get really close to the y-axis. So there's the first part. If I were to plug in -1, would that work? Well, -1 squared is 1. 1 divided by 1 is 1. And then multiply it by 4, still puts me over here. So this one's symmetric over the y-axis as well. So I'll just copy these 2 points in and draw in the function. Cool. Let's talk about domain, all this junk. So the x values that won't work, well, x can't be 0, but it can be negative. So I would say x just can't be 0. The range. Y has to be over the x-axis, so y has to be bigger than 0. I'm not going to say it can equal 0 because this is going to get really close, but it's never going to touch. X-intercepts, there's none because it doesn't touch. Y-intercepts, there's none because it doesn't touch. Increasing, so when is it going uphill versus when it's going downhill? From left to right, it's going uphill from -infinity to 0. Decreasing, it's going from 0 to +infinity. Symmetry. There is symmetry because it is an even exponent. It's going to be symmetric about, oops, the y-axis. Or you can just write y-axis. Discontinuities, yeah. We have to pick up our pencil, right? So we're drawing and it's going up to infinity, then you have to pick up your pencil, put it back down on the other function, and drop down. So at x equals 0, there's an infinite discontinuity. Infinite. End behavior. As x approaches +infinity, y is approaching 0. It's not going to touch 0, but it's going to get really close. As x approaches -infinity, it's also y is also approaching 0. And there's that. Let's do another one. No, let's do 4 more. Okay, so this one we're going to do a rewrite. It's -1 over x to the 5th. So we have a negative odd function. Negative odd. So we look over negative odd, it's going to look something like this. I already forgot what it was going to be. That one. Since it's negative odd, it's going to be symmetric about the origin. And let's just start plugging some values in. I can't plug in 0, because if I put in 0, I get 1 divided by 0. That doesn't work. We do the next one. 1 divided by 1 to the 5th. Well, that's just 1 divided by 1, but we want to make it negative. So it's going to be right here. If I plug in 2, well, that'd be 1 over 32 and negative, so 132 would be some tiny fraction. If I put in 1/2, I get 1 over 132, which is the same thing as 1 times 32 over 1, or 32, which would be actually negative because we have negative in front. So that means at 1/2, it's jumping way down to 32 on the y-axis. So it's getting really, really tight there. Tight right here. I'm just going to copy these 2 points in. So we got this one right here, this one, that 1 over 32-ish. Okay, the domain. It looks like x can be anything but 0. And the range, yeah, y as well, can be anything but 0. There are no x-intercepts, no y-intercepts. It's increasing from -infinity to 0, and this one is also increasing. So we're going to go also from 0 to infinity. We have to put 2 here because we're not including this value of 0. So it's basically hopping over 0 is what this one says. Decreasing, there's none. Discontinuities at x equals 0, there's an infinite discontinuity. End behavior, x approaches infinity, x approaches negative infinity. Ooh. As we go to positive, it looks like it's approaching 0. So go to negative, also approaching 0. And that's it. So this is going to be rewritten as 3/2 times 1 over x to the third. It's positive, and it has an odd exponent. Positive and odd. Let's go flip and look at our end behavior. Positive, odd, that's like our parent function looking like. So this one's gonna look something like, oop, oop. Let's plug in some values. So if I plug in 0, oh, I can't plug in 0 because 1 divided by 0 doesn't work. So I gotta plug in 1. 1 over 1 to the third is 1. 1 times 3/2, which would be just 1.5, so I put a dot right there. I could plug in other values like, 2 to the third would be 8. This would be 3 over 16. 3 over 16 is a really tiny fraction, so it's getting really close to the x-axis. So here's my first picture. I'll do it again on the other side. So it's bouncing off to the other side here. If I put a -1, 1 over 1, -1 to the third would be 1 over -1. We'll just make this negative. So we're gonna go 3/2, and then a tiny fraction. There's our picture. Domain, it looks like x can't be 0 again. Range also can't be 0. Did I say x can't be 0? I meant y can't be 0. There are no x-intercepts, and there are no y-intercepts. Increasing interval, it looks like it's not ever increasing, but it is decreasing from here and from here. There's 2 parts, so we're going to go negative infinity to 0, and then 0 to positive infinity. It's symmetric about the origin. A big takeaway of how you know it's going to be about the origin is if it's odd. Just like this one was odd. Meaning their tails are going to point different directions, so there's no way it can be symmetric about the y-axis. Discontinuities, it has an asymptote at x equals 0. In both cases, as we go to the right, it's getting close to 0. As we're going to the left, it's getting close to 0. So I'm going to do a rewrite. This one looks like -2, 1 over x to the 4. So that one is a negative and even. So if it's even, that means it's going to look something like this or this. But it's negative, so it looks like it's gonna face down. Let's double check. Negative, even. Negative, even, yep, it's facing down. So it's gonna be this one. Let's plug in a value. Can't plug in 0, but I can plug in 1. 1 over 1 to the 4th is just 1 times -2. So we're gonna put a dot right here. If I plug in other values, I'm sure I would find more details, but this is just gonna get really close to the x-axis and really close to the y-axis. There's that one, and it's a twin on the other side of the y because it is symmetric about the y-axis. The domain, it looks like x just can't be 0 again. Range. Range has to be everything under the x-axis, so everything less than 0. I'm not saying or equal to because it doesn't touch the x-axis. There are no x-intercepts and no y-intercepts. In all these situations, we've had no x-intercepts and no y-intercepts. That would change if there was something like the function moved to the left or moved to the right, therefore moving our asymptote left or right. So be careful, it's not always going to be none. Increasing, it is decreasing then increasing. So it's increasing from 0 to infinity and decreasing from negative infinity to 0. Discontinuities, once again, we can't have x equals 0. So at x equals 0, there's an infinite jump. Not jump, but infinite discontinuity. And behavior. As x approaches infinity and x approaches negative infinity, y will approach, it's going to the right, y will approach 0. Going to the left, y will approach 0 again. All right, last one. We've got a negative 1/4 times 1 over x to the 6. So this is negative even again. So if it's negative even, it's going to look like this one. So it's going to symmetric about y-axis. If I plug in a 0, it won't work, but if I plug in a 1, get 1 over 1 times negative 1/4, so it puts me like right there. It is decreasing from negative infinity to 0. Increasing from 0 to infinity. There are none. None. Domain, x can't be 0. In this case, y has to be smaller than 0. And we're done. See you tomorrow.